So like I said before, what we're going to do is look at where we were and where we're going to. So what we did in the past was talk about separation of variables. So it's important that you understand what it means to separate a variable. So to separate a variable means to take the x's and the y's and break them apart. So what makes the equation here a differential equation? A differential equation involves a dy dx. So a differential equation involves a dy dx. It is essentially, I missed the word is, it is a derivative. So what makes something a differential equation? It is a derivative. So when you hear or read the word differential, all you're thinking is that you have a derivative. Okay, our goal is to take that equation and rewrite it as y equals. So what we can't do right now is write it that way because x and y are together. So what we're going to do is take that equation and separate it. So because we have to have dx with our x's and dy's with our y's, we have to mix them up. So what we're going to do is say dy equals x over y squared dx. And that still, at that point, isn't integratable because the y squared's with the dx's. So you multiply both sides by y squared. And you have y squared dy equals x dx. Oops, sorry, that final step should have been in 3. I jumped ahead of myself. So it says, how do you accomplish this? By putting the y's and the x's on opposite sides. Once the variables are separated, you can integrate both sides with the general solution. A general solution means that you are going to have a plus c. A general solution is going to occur when an integral has no bounds. So a general solution occurs on an indefinite integral. So I think a part of our issue on our mock exam was just seeing these words and terms out of their context and not being able to, totally fully comprehend. So differential means derivative. General solution implies plus c. So you're going to integrate y squared dy equals the integral of x dx. So again, if you're asked for general solution, you're integrating. So our rule is to add a power, divide by that power. And then it's in general, so you have your plus c. And then we want to solve for y. So we're going to multiply both sides by 3. Remember, the 3 doesn't distribute to the c just encompasses it. And then to get rid of something cubed, we're going to cube root it. A cube root is not like a square root. We do not need a plus or minus with a cube root. You do not need a plus or minus with a cube root. Yes. Yes. So what we're going to be focusing on today is looking at more complicated differential equations as well as some laws involving some terms. such as Newton and Decay. So in order to be able to do that, we really have to be able to do this. So again, it's saying differential, that's implying the derivative. Initial conditions, those are going to take the place of your C, and you want to find y equals. So in order to find y equals, we have to separate apart our variables. So we're going to get dy dx so that the y's are on the left and the x's are on the right. In order to do that, you're going to have to take out a GCF of x. So that would leave you with y plus 1. So now I can get the y's on the left and the x's on the right. And once my variables are separated, now I can integrate. Anytime you have a function under 1, it's going to be an ln. So this is going to be the natural log of the absolute value of y plus 1 equals 2x squared over 2. So your 2's cancel, plus c. Now personally, I like to find the c value now, then solve for y. So at this point, I like to find my c. I think it's easier algebraically. Usually the natural log works out to be something sort of simple. So we have the natural log of 2 plus 1 equals 1 squared plus c. So the natural log of 3 minus 1 equals c. And we're going to just plug that in and use it throughout the course of the problem. So now we're going to solve for y. So you have ln y plus 1 equals x squared plus natural log 3 minus 1. To get rid of a natural log on the y, we're going to e both sides, which means everything over here on the left becomes a power of e. So you get left with y plus 1. And that y plus 1 remains inside our absolute values. And you're going to see why in a minute here. Equals, now if you recall your rules for exponents, a to the m plus n, so any base to an m plus n is equal to the a to the m times a to the n. Because the rule is that if you have like bases, you add your powers together. So what that means is I can really rewrite this as e to the x squared times e to the ln of 3 times e to the negative 1. And the reason I want to do that is think about e ln 3. That's going to cancel. So e to the x squared and e to the negative 1 are going to stay. But that e ln of 3 is going to come out in front as a constant. So I'm left with 3e to the x squared minus 1. Now to get rid of your absolute values, if you think about how we got rid of them back in the day, we turned it to a plus or minus because we said the absolute value represents both sides of the solution. So this is like saying plus or minus 3e to the x squared minus 1. And then to isolate y, you subtract 1 from both sides. And there is our differential equation that fits that initial condition. I have no idea why your screen keeps doing that. It's saying the network is low. Don't know how to fix that. Okay, so let's look at one more case in which we have to separate and we have an E or an LN type part of our problem. Here, the key part is it passes through the origin. That's like telling you this goes through 0, 0. So instead of directly giving you that initial condition, it's implying pieces of information about that initial condition. It says find the particular solution to the differential equation. So what we're going to do is separate our variables. So again, using our powers or laws that go with exponentials, this is really like saying dy dx equals e to the x over e to the 2y. Because the rule is similar to the a to the m plus n. It's kind of like saying a to the m minus n is the same as a over m and a over n. Now we can cross multiply. We get the e to the 2y with dy. We get the e to the x dx. And then we integrate. This is kind of like a u sub because it's something other than x. So that's like saying u is equal to 2y. Du is equal to 2 dy. So what are you missing in your problem? You're missing the 2. So this is kind of really like 1/2 e to the u du. So it's 1/2 e to the 2y equals e to the x plus c. So you just got to make sure you take into account that 2y is going to give you the 1/2 in front of that e. Once again, I like to find my c value now. So I'd say 1/2 e to the 0 equals e to the 0 plus c. E to the 0 is always equal to 1. Good. So you'd get 1/2 minus 1 equals c, or c is equal to negative 1/2. So then you solve for y. So you have 1/2 e to the 2y equals e to the x minus 1/2. So we're going to get rid of our 1/2 by multiplying both sides by 2. And then we're going to get rid of the e by ln'ing. And then the last thing is, since it's 2y, we're going to divide both sides by 2. And you could write that 2 out in front, or you could write it underneath. So the last part of that problem was a piece or a screenshot of an AP question. So we're going to skip this page for now because it's in your other notes packet, so you don't need that. What I want you to do is take a minute. This is only part A of a prior AP exam. And before we look at the 3 different students, I want you to look at this and try to say, okay, how could I do this? So it's a differential, which means it's a derivative. You're supposed to find y equals given this initial condition. So go ahead, take a minute and work that out on your own. And then we're going to go through and look and find errors the other students that did this on an AP exam made. Or the AP student. So, first things first, separate your variables. Take your integral. Then find c. So we should have gotten a c value of 1/2 e. Then you multiply by 2 and solve for y. So I got y equals 1/2 the natural log, absolute value 2x cubed plus e. So that's my answer. Look at your answer and look at the next 3 pages and see if you can find an error you made and an error any of those students made. So we know that this is what the answer should be. Now look at their work and your work and see if you made any mistakes. And this would probably be a 3 or 4 point question on the AP test. Okay? So, what error did this student make? They made an error. What did they make? Go ahead, Bethany. Perfect. So right here, they forgot absolute values. Okay, how about on the next page? What error did this student make? The one didn't add a C. Wonderful. So right here, we're missing our C. What about over here? This one's a little trickier. There's actually 2 errors. All right, Maddie? Correct. So right here, this antiderivative is incorrect. And by technicality, this is like incorrect notation. We can't have dy dx inside with an integral like that in meshed up variables. Because they're also saying this is y. They said like that's y equals, and we know that that's kind of like iffy too. Okay. So what I want to do now is, that's sort of the conclusion of that. I want to pick up with the new set of notes, but I want to give you guys like a few minutes to stretch out and breathe. Did you want to take our loop outside again, or do you want to stay? Yep, let's go take our mask break and loop. All right, so there are, again, other ways of writing sentences, looking at things. So it says, determine whether the given function is a solution to the differential equation f double prime of x minus f of x could equal 0. So you were given f of x. So how could you prove that statement? Well, in order to prove that statement as being either true or false, what you would need to do is then take that problem and find the second derivative. If it's asking me if the second derivative minus the original is equal to 0, in order to be able to prove that, I need the second derivative. So the derivative of sine is cosine. The derivative of cosine is negative sine. So that statement becomes negative sine x minus sine x, which does not equal 0. So to determine whether that function is a given solution, that would be no. F of x is not a solution. Letter B, we have to find f prime. So again, we're doing this to help review our derivatives. It's been a while since we really focused on derivatives. So the derivative of 4e to the negative x, the 4 tags along. You multiply by the power, which is negative 1, and then e to the negative x. So you get negative 4e to the negative x, but we have to take that derivative again. So it's negative 4 times negative 1 e to the negative x. And a negative times a negative is a positive. So we have 4e to the negative x for our second derivative. So that means that this is 4e to the negative x minus 4e to the negative x, which does in fact equal 0. And letter C, the derivative of that would be equal to c e to the x. The derivative of that would be equal to c e to the x. So a constant in front of an e to the x becomes the constant in front of the e to the x over and over and over and over and over again. So the derivative of e to the x is one of the unique functions where its derivative and graph will look exactly like the original. So you'd have c e to the x minus c e to the x, which we know would in fact equal 0. And that all has to do with the property of e to the x and the fact that it is a duplicate of itself. Okay, number 2. So I think slope fields are still something we have to focus on. So it says shown to the right is a slope field for which of the following. So this is a multiple choice slope field question, and what you're trying to do is determine, okay, which one of these equations make it true. So one of the easiest ways to go about figuring that out might be just to pick some points on your graph. So you could pick really any point you want, and then you would look at the slope of the line. So maybe I decide to pick negative 2, positive 2. And at negative 2, positive 2, I see that the slope of this line is positive. So what I'm going to do is plug in negative 2.
Ryan Priest, please report to the office. Ryan Priest.
2. So negative 2 plus 2 is 0. Negative 2 minus a minus 2 would be a negative 4. A negative times a negative would become a positive. So that would be 2 plus 2, which is positive 4. A negative number squared is positive. So that would be 4 again, minus 2. So 4 minus 2 would give you a positive 2. So looking at that slope field right there, the minute you got 0, A was eliminated. And the minute that we got negative 4, B was eliminated. So we could do this again and try to determine if it's C or D. So what you would want to do for C is that's dy dx equals negative x plus y. So maybe we pick a point where we have 2 positives now. So maybe I pick 2, 2. And what I notice here is that the slope is 0. So negative 2 plus 2. And here 2 squared is 4. 4 minus 2 is 2 again. So letter C gives me the slope of 0 I was looking for. Therefore, this is a slope field that matches letter C. Okay, and then example number 3, given the differential equation with a particular solution, find the y equation. So once again, this is like what we've been looking for. We're given a differential equation and we want to find the y value that is going to make that initial condition true. First things first, get the x and y's apart. So I would probably start by dividing both sides by y. And then I would also divide both sides by x squared plus 4. And then multiply by dx. So you have 1 over dy dy equals x over x squared plus 4 dx. In order to integrate this, you have to consider that this is a u substitution because you have an x squared on bottom and an x on top, and on bottom you have addition. So that would be like saying u equals x squared plus 4. Du equals 2x dx. So the 2 is extra. So then this becomes 1 over y equals 1/2 the integral of 1 over u du. And the antiderivative of 1 over y dy is the natural log of y. And then the antiderivative of 1 over u is also the natural log of u. Don't forget your plus c. So you have the natural log of y equals 1/2 the natural log of u plus c. Remember, all natural logs, when we do our integration, get absolute values. So there's absolute values around both the y and the u. And then what we're going to do from here is replace the u back with its original function of x squared plus 4. And then you have a decision to make. You can use the initial condition now to find c, or you could find y by itself and then have to go back and find c. So like I said, I have a tendency to plug it in before I both sides. So I would say, okay, I have the natural log of 2 equals 1/2 the natural log. Negative 3 squared is 9. 9 plus 4 is 13. Plus c. And then technically the 1/2 power could come in as an exponent, or, so again, you have lots of choices, and that's what I like to talk about. You could subtract the natural log over and say minus, which I think is the decision most of us would make, minus 1/2 natural log of 13 equals C. And if you recall, our rules with subtracting is that that's really like division of the insides, but that's where bringing that 1/2 in would be important. So it's kind of like saying the natural log of 2 over 13 to the 1/2 power equals C. Yes. I don't know why it continues to do that. It was fine all morning. Maybe I'll just... All right. So then I go back to this step here. And in order to get rid of the natural logs, I would E both sides. And again, take into account that if you're adding them, that's like multiplying with the e's. And then the natural logs are going to cancel. And that's going to come down as your C value. So you have 2 square roots, 2 over the square root of 13. E to the 1/2 natural log x squared plus 4. Okay. Any questions or concerns having to do with that? So again, I know that these are lengthy, but again, you saw on your mock exam, there is typically a problem like this on the AP exam in which you have to find a solution. Some of the other applications that we will see, and again, we're going to skip this one because we've done so many. I want to look at today is growth and decay. Because that's something we haven't talked a lot about for a while, but that this is more of the application aspect that you might see involving these separated variables. So this in our textbook, we're actually looking at unit, if you want to know, because you like to know, this is 6.4. In our book, we are in unit 6.4 right now. So oftentimes, physical phenomena can be described by differential equation. For example, problems involving radioactive decay, population growth, and Newton's law of cooling can be formulated in terms of an equation that contains a derivative. Remember, a derivative is simply a rate of change. So in these applications, the rate of change of the variable y is considered proportional to the value of y with respect to time. So this is what the one problem on your mock exam was, where it talked about the growth of the trees being proportional. that proportional statement was dy dt, and you had to incorporate that 0.003 back into the problem, and we all sort of lost that 0.03 or didn't know how to include it. Mainly because we're going to talk about it today. So dy dt represents a rate of change of y proportional to y, where k is the constant of proportion. So we call k the constant of proportion, and we say that dy dt is our rate. So in exponential growth or decay, we have that this rate is proportional I'm printing them. So y is equal to ce to the kt. So y equals ce to the kt. C is what we call the initial value. It's kind of like our initial condition. It represents this exponential growth or decay. If k is positive, we have growth. If it's negative, we have decay. And that should make sense even in terms of our derivatives. If you think about a function being positive, then you have an increase. If a function is negative, then you have a decrease. So here we have our half-life. These are actual real-life data. This is actual real-life half-lives. So we've talked about this probably in science classes, where you talked about these different elements and how they exist. And one of the wars in 1986, there was a nuclear accident where all of this radiation was put out into the ground. And so this problem says, suppose that there are 15 grams of this isotope that was released during the Chernobyl nuclear accident. How long will it take for 15 grams, so that's the initial, to decay? So that tells me my K value is negative. And this is what we are trying to find. We are trying to find how long it will take to get to 1 gram. So basically what we're going to do is use that idea of dy dt equals ky, the idea of y equals c equals kt, and we're going to use that to come up with a solution to this problem. So we're going to fill in what we know. What we know is the initial. So the initial condition is that at year 0, there is 15 grams. And we're going to use that to find C. So we have y equals ce to the kt. So this is like my t and my y. So that's 15 equals CEK times 0. Well, anything to the 0 power is 1. So C is equal to 15. And that should make sense because this could also be written as y naught e to the kt, where y naught stands for y initial. And we were told that the initial amount was 15 grams. So that stands for your initial or your t equals 0 value. So my equation is y equals 15e to the kt, and we are trying to find how long it will take to decay to 1 gram. So what we need to do is find k. And in order to find k, we need to use the half-life from above. Typically, on a problem on the AP exam, they would tell you the half-life of its value. So it says that its half-life is at 30 years. So what that means is that if t initial is 15, t equals 30 would be half of that, or 7.5. So it would take 30 years to get to 7.5. And we get that from our table up above that tells me its half-life is 30 years. So what that means now is that y is equal to 7.5 when t is equal to 30. So we divide both sides by 15. And then you have e to the 30k. So how do you get rid of e? You ln both sides. So we're going to ln both sides. And 7.5 over 15, well, that's kind of like 15 over 30, which is 1/2. So we get the natural log of 1/2 equals 30k, or the k is equal to the natural log of 1/2 divided by 30. So now my y value is y equals 15e to the 1/30th natural log 1/2 t, because this represents k. And now we want to know, when will we be at 1? So the last thing we're going to do is say 1 equals 15 e to the 1 over 30 natural log 1/2 t. So you ln both sides to get rid of the e. You can multiply both sides by 3 and divide by 1/2. And then again, we know that our natural log of 1/15th, natural log of 1/2. This is all sort of just represented. Sorry, that should be 1/30th, and then that should be a 30. Sorry, I dropped my 0. We're just going to multiply this to get a number. And whatever that number is, that number will represent the number of years it takes. So you would just do 30 ln 1 over 15 and then divide that by the natural log of 1/2, and we get 117.206 years. So what that means is if this happened in 1986, you'd have to add those years to 1986, and not until the year 2103 can people go back there and have safe drinking water. So well beyond my time for sure. So back at the beginning of the year, we actually started with a fruit fly population question. And we're kind of summarizing and getting to a point now where we're going to use that same type of question, but we're going to use it with growth and decay. So it says an absent-minded graduate student is studying the population of fruit flies in a lab. She works under the premise that fruit flies increase according to an exponential law of growth. She counts 100 flies after the second day. So that's kind of like 2 100. And 300 flies after the fourth day. So that's 4 300. However, she forgot to record the number of fruit flies initially. At the beginning of the experiment, approximately how many fruit flies were in the original population. So what we can do is take that same idea of y equals y naught ce to the kt, where y naught is my initial, and go backwards and figure out, okay, what was the initial population? So we know that at 100, E was equal to 2K. So we have 100 equals CE to the 2K, and we have 300 equals CE to the 4K, and C and Y naught mean exactly the same thing. That's why when I accidentally wrote C over here, I scribbled it out. Y naught and C are the same. They all represent that initial population. So what could I do to kind of get to a point where I could solve for K? So if you had two variables and we have two equations, what's a technique we learned in algebra to solve for one of our variables? Go ahead, Maddie. Yeah, kind of like a system of equations. So if you think back to systems of equations, our two methods are substitution or elimination. So what I would do is solve each of these for C. And then you could do a system of equation where you either eliminate C or you substitute one with the other by setting them equal. So you have e to the 4k equals 3e to the 2k. So I would divide both sides by e to the 2k. And then again, your rule of thumb is that you have like bases, you subtract the tops. So that would give you e to the 2k equals 3. How do you get rid of e? You ln both sides. So you get 2k equals the natural log of 3. Divide by 2. And we get k equals the natural log of 3. Divided by 2. So then you go back to your original equation here, and we have y naught equals e. Now we know k is the natural log of 3 divided by 2. Now we still don't know y naught, but what you can do to find y naught now is pick either of your initial conditions to solve for it. So you could say 100 equals y naught e to the natural log of 3 divided by 2 times 2. And I mean, it's nice because your 2's cancel, the e's in the ln cancel, and you get 100 equals 3y naught, or that y naught equals 100 divided by 3, which means that there were approximately 33.33333 repeating fruit flies to start the experiment. So again, just to give you guys a little bit of a break, we'll skip 4. I want to hit Newton's law of cooling because sometimes there is a cooling law on the AP exam. And again, like I even have like a note. It's not specifically like called a Newton's cooling law. They like sort of give you this word problem. And you have to take into account an initial temperature and an experimental temperature. So what happens is that our temperature and our environment affect our total temperature. So if a good example of, what? Did I imagine that? Maybe. So a good example is a hot cup of coffee. So if you take a cup of coffee and you pour it out, the environment is colder than the cup of coffee. Therefore, your coffee is going to cool with the environment. CSIs use the temperature of a room and the temperature of a dead body to determine time of death because they can figure out when the body temperature was 98.6 degrees approximately and how long the body cooled to get to its current temperature. So Newton's law of cooling is actually applied in a lot of real-world situations where it can be used to determine other types of conditions. So we're going to do it with a less kind of creepy condition, and we're going to look at a pastry chef removing a cake from the oven. So it says it's placed upon a cooling rack in a room whose temperature is 60 degrees. That's pretty chilly in my opinion. Using a cooking thermometer, he determines that the cake cools from 100 to 90 in 10 minutes. The icing cannot be applied till it reaches 80 degrees. How long does he need to wait? So we're going to let capital T represent the temperature of the cake. And then we're going to use the equation from up above. where T initial represents the temperature of the cake when it is removed. And then dt is going to represent the temperature of the cake that we want to apply it to. So, and TE is the temperature of TE is the temperature of the room. So we know that TE is equal to 60. So plugging in everything we know to that equation, we have dt initial over dt equals K, T initial minus 60. And we're going to get the capital T's together, and we're going to get the little t's over here. So I'm going to divide both sides by T naught minus 60 and multiply by dt. So Newton's law of cooling is one of the first ones where we can actually see an application. If we have a dt naught and a dt, we're going to integrate. This is a natural log because you have subtraction of a variable down in the denominator. So you get the natural log of T naught minus 60 equals KT plus C. Because K is just a constant. dt is your variable of integration, which means you add a variable back. Then we can use the initial idea that we had 0, 100, because that was the temperature when it became out of the oven. So you'd have the natural log of 100 minus 60 equals K times 0 plus C. And our constant of integration is natural log of 40. And we can use that idea to find K. So we're going to use that at 10 minutes, it was at 90. So you get natural log 30 equals 10K plus natural log 40. So subtract your natural log of 40 from the natural log of 30. Which is really like minus 40, which is 10. Or, sorry, 30 divided by 40 because subtraction becomes division, where it's the opposite of exponential. So it's really like 3/4. And then we're going to divide by 10. And there's our K value. So our equation is ln T naught minus 60 equals ln 3/4 divided by 10 T plus ln 40. So if you want to know when will the cake be 80, you plug 80 in and solve for T. So 20 minus 40 is like 2/4, which is like 1/2. And then you would divide that by ln 3/4 and multiply by 10 to solve for t. And use a calculator to find that time. Which is 24. So what that means is it takes approximately 24.094 minutes to cool to a temperature at which he could ice the cake. So if that said how much longer does he have to wait to ice the cake, he doesn't have to wait 24 minutes longer. He's already waited 10. So to answer that initial condition, Bernie must wait, and this is where AP tricks us, 14.094 minutes longer to ice the cake. Because again, he's already waited the initial 10. Okay, so your homework is a mix of textbook and worksheet. So you are going to do the differential equation Big 10. So that's 10 problems. And then in our textbook, we're going to do a couple problems from this unit. So you're going to go to actually the end of the chapter. We're going to go to the Chapter 6 review. And I'll tell you that page number here in a minute. So you're going to go to the end of the chapter. You're going to go to the Chapter 6 review. And you are going to look at 28 to 42 even. 28 to 42 even. Skip 36. So 28 to 42 even, skip 36, and then 51 and 52. So you're going to the Chapter 6 review. (28) to 42 even, skip 36, and then 51 to 52. I did the problems but didn't write a page number. So it's on page 373. 373. What are you looking for?
I didn't get a Big 10 worksheet.
It was in the, no, it's in the packet we started class with. It's after the AP problems that we went over and found the errors.